good afternoon, good morning, good evening, wherever you're at. Welcome to Data Engineers Lunch number 26. So my face here. Let's go ahead and get this started. Thanks, Josh, for helping with the recording. Can't believe we've been doing this for more than 6 months now, actually. Today's topic is Akka Actors for data processing. Akka is one of those technologies that, next to functional programming, only true computer science geeks love, like me. Even though I don't like to program, I love how actors work. So I'm really excited about today's topic because I also like data processing. Nikita is a software engineer here at Anant, and I'd love to see his progression. We've done a few presentations on this in the past. Today, I'll be emceeing. Thank you, Arpin and Josh, who've been taking ownership of this group and helping put on these events in the background and sometimes in the foreground. So thank you, guys. Always looking for more help to help get sponsors and members. We're part of a larger community of data practitioners in the DC area, very diverse. We'd love to have folks from different backgrounds come and speak. If you know somebody who can speak about any of the things we talk about, please either volunteer them and we'll contact them, or tell them about us. Data Community DC, as you can see, is made up of many different groups around the topic of data. Some of it's data science, some of it is visualization, some of it is full stack data science, which is obviously everything around the application that is using the data science. We cover the engine, data engineering, data wrangling, that makes all this stuff work. And data engineering is been around for a long time. So there's a lot of different technologies, a lot of different frameworks, a lot of different ways to do it. But ultimately, if you get your shit together, problem that we solve here. Get all your data in one place, clean it up, and give it to somebody else. Usually at this time, we ask for people to introduce themselves who haven't been to our group before. I think Sujay Shankar, do you want to quickly introduce yourself, if you'd like? Otherwise, we can pass. Okay, no. All right. Well, looks like the rest of us are regular attendees here. Group rules. If you have a question, just ask it. Be polite and courteous to others. Share what you know you don't have to have a question. You can just share it. Our speaker might have a different approach to this, but generally we like a conversation. You can also ask questions or share comments in the chat. Our company is boutique software consulting company, data engineering and data operations company. Actually, software is part of all of that stuff. We focus on helping people build platforms that are global, help serve large, impactful causes. We focus on Cassandra, Spark, Kafka in terms of the technology stack. DataStax is a sponsor and a partner. So is GW University, the George Washington University. We are also in DC and Chicago. We have a couple of local sponsors. And we have organizational sponsor for all of Data Community DC that help us run it as a nonprofit, actually. Any jobs or announcements from the group? Okay. Well, we're always hiring platform operators, data engineers, data architects. DevOps is a bit of that as well these days. You can go to careers.anant.us. Upcoming events, Cassandra.Link should be 3 in a few days. That's a milestone. That's more than a year of Cassandra.Link. That's great. And then I will be presenting something next week. I don't know what, but I'll tell you when I show up next week. We have monthly events on Data Community DC. A lot of the groups have their own meetup pages. We have data wranglers every week, every Monday, same place, same time. You can also check out events at anant.us/events. And without any more admin trivia, I'd like to hand it over to Nikita, our speaker for today.
Thanks a lot, Raul. Yeah, I'm Nikita, engineer here at Anant. Let me share my screen really quick. 1 second. Hopefully this is the right thing. Is this visible? Does it look fine?
Yeah, you can see it.
Cool. And yeah, today I'm going to talk a little bit about the actor model, about Akka's implementation of the actor model, and show off a very basic data processing demo application. All right. So the actor model is proposed by Carl Hewitt in 1973 as a way to handle parallel processing in a high-performance network. So back when this was proposed in 1973, such a high-performance network did not exist, and the need for parallel processing was not particularly there yet. But as it's year 2021, this has significantly changed, and our systems today and how powerful our computers and CPUs are far exceeds what Carl Hewitt probably ever thought could exist. So the actor model is actually relevant nowadays. So in computer science, the actor model is a mathematical model of concurrent computation that treats an actor as the universal primitive of concurrent computation. So in response to a message it receives, an actor can do a number of different things. It can make local decisions, so do some kind of calculations, do whatever it needs to do. Every actor can create more actors. Also, every actor can send messages. And also actors can modify their behavior to decide how to respond to future messages. So one very important thing about actors is that they may change their own private state, but can only affect other actors indirectly through sending messages, which is awesome for a large number of reasons. And the actor model can be used as a framework for modeling and understanding a wide range of concurrent systems. So for example, you can think of email, like email in general, as an actor system with individual email accounts as actors and email addresses as actor addresses. And then they message or email each other. So what is Akka? Akka is a free open source toolkit and runtime for making concurrent and distributed applications on JVM, or Java Virtual Machine. Akka's approach to concurrency is based on the actor model mentioned on the last slide. And Akka is written in Scala, but can be used with either Java or Scala. And then, besides the ability to easily create and interact between actors that Akka provides in the Akka-actor module, there are also plenty of other modules in Akka which are built to work alongside Akka's actor system. So I'll mention a couple here. Akka HTTP, which is a full server and client-side HTTP stack on top of Akka Actor and Akka Streams. Akka Streams is a library in Akka which is used to deal with processing a sequence of elements using bounded buffer space. And there exist a lot more Akka modules and libraries that can be found in the documentation. But one we've already discussed about, or I don't know, maybe a couple months ago on Anant's Cassandra lunches, is Alpaca, where we talked about using Alpaca Cassandra to interact with a local Cassandra database on top of Akka Streams, which is pretty cool. So there are a lot of things that the actor model and Akka Actors implementation of it can solve that you run into when doing traditional object-oriented programming. I'm going to talk about one of those things. So one large motivation for creating Akka and a problem it resolves in the OOP model is a problem with encapsulation. So objects can only guarantee encapsulation, protection of invariance in the face of single-threaded access. However, in multi-threaded programs, multiple threads can go inside of the same object at the same time. And so this can cause a corruption of state, and nothing is guaranteed about what happens to the method/object that multiple threads are accessing and modifying at the same time. So for example, if I have some object that I'm using to just count something, and then I have some method that is like method add one to counter or something. And then if two threads go in at the exact same time, or at a very, very similar time, they can both basically set the count to, oh, the current count is 80. I'm going to say the count should be 80 plus 1. And if they do it at the same time, then the count will still be 81. And so you didn't count both actions properly. And so one way around the above mentioned issue is locks, which is restricting access to all other threads if a thread is inside a particular object or method. However, without sufficient locks, state may still get corrupted. And with a lot of locks in place, performance suffers significantly, and this can also lead to deadlocks, which is when a set of locks are active in such a way that the program cannot continue doing anything. So there's a little picture I've added here in the presentation at the bottom, where we have two resources, resource 1 and resource 2. One thread is currently using resource 2, and thread 2 is currently using resource 1. And thread 1 wants access to resource 1, but resource 1 is being used by thread 2. And then thread 2 wants access to resource 2, which is currently owned by thread 1. And so basically you're at a standstill here, and your program won't continue. This is a very simple example, but these things do happen when you're building large applications with locks set up either improperly or incorrectly by accident, or sometimes by design. And then with Akka Actors, an actor reacts to messages that are sent to it sequentially and one at a time. Since there's always at most one message being processed per actor, the invariance of an actor can be kept without synchronization. This happens automatically without locks in Akka. So on the left, we're showing off two threads, which are the red and green lines, trying to interact with object 2 through method A. And we can see that there's a period of time where it's possible that both of them are inside object 2 at the same time. And so that's where we can run into issues. And then on the right, we show off what happens in Akka when you have actor 1 and actor 3 trying to interact with actor 2. And so again, the only way actors can interact with each other is through messages. And so they both send messages. So message A arrives first, message B comes in after. So message B is put into like a something I believe Akka refers to as a mailbox for actor 2. Then message A is processed, and then after message A is processed, then message B gets dequeued from the mailbox and then actually starts being processed by actor 2. So you won't run into issues like on the left, which is pretty cool. Another thing I want to briefly mention is Akka's classic actors versus typed actors. For quite a while, Akka actors used to be untyped, which is now referred to as classic actors. And so what that means is the actors are defined which accept messages of type any in Scala, and then pattern matching is used to determine what messages that particular actor actually will process. And so basically, unless you manually code into all of your pattern matching, like specific issues, if you've sent like specific incorrect messages, Wrong messages can be sent to actors with no explicit error thrown by Akka itself. And so that's not good when you're writing things to be used and potentially modified by other people or by multiple people or just by even yourself, but over a large period of time where you might not remember all aspects of the thing that you're working on perfectly. One reason I mention these classic actors is that a lot of existing examples of Akka programs are still written with classic actors. So very often, or for a lot of resources that you'll find online, they will look even completely different from my project. And that's because they're probably written with older classic actors. Akka's current version of actors is referred to as typed actors. So this is unlike untyped actors. When making an actor, their behavior is typed, which tells you what kind of messages a particular actor can accept. Additionally, references to actors, known as actor ref, are also typed, which helps a user send only particular types of messages to a given actor, which is good. And although using Akka's typed actors is now recommended, programs which currently use classic actors are still supported, and the two types of actors can actually coexist in the same program at the same time. In Akka documentation, this is referred to as coexistence, and you can read more about it in the docs. All right. And sorry about that. And this project is built with SBT, which SBT is an interactive build tool for Scala and Java projects. A large majority of Scala projects are built using SBT, and the demo project is no exception. More info on SBT can be found at their website. So now I'm going to talk a little bit about the sort of the actor structure of the demo project, what it does, and then we can go into it briefly. The link to the GitHub repo is still TBD, but we'll have it up by the time this goes live on YouTube and when the blog post comes out. So I've drawn a diagram on the right. Hopefully it's large enough. But basically what it's showing is that we're going to be reading in some kind of data from files. So in our case, it's going to be just text files, but it can be whatever you want. And then this data goes into our main application. And then the circles here I'm using to represent actors that we're going to be making. So our main application is going to read the file. And then for every line that's in the file, we're going to send an initialize message. Or first, rather, we're going to spawn our counter main, which is our sort of main actor in the system. And then we're going to send it a bunch of messages that contain individual lines of the file. From here, when counter main is first initialized, or rather, first spawned, it's going to spawn one aggregator bot, and then that bot is just going to sit there for a bit. And then as messages come in with lines from the text file to counter main, it's going to spawn a counter bot for each one of the lines. And it's going to send them a line message. And the line message will contain two things. It will contain the text contained on that one individual line that bot is going to process. And it also is going to contain an actor ref to the aggregator bot, so that once our counter is done, or once each of our counter bots are done doing whatever they need to do with their given line data, they can then send a count message to the aggregator bot, which, as the name implies, will put all of this data together, and we'll have a wonderful result. So in this case, what we're doing is we're going to be counting the number of words in a file. This is a simple example, but given the structure of the code and the fact that everything works, this can be extended into doing all sorts of data processing. Like instead of sending individual lines to every one of the counterbot actors, we could send them like entire files or sets of files even, and then have them do some kind of processing and then send it off to our aggregator bot to do whatever aggregation is necessary for any other kind of project. So going to open up demo file. 1 second. I probably need to increase the font size. Yeah. I should have done this beforehand. 1 second. Change the font size to like 30. Is this large enough?
Yeah, it looks good.
Okay. So again, just to reiterate, we have 3 different types of actors in this system. We have a counter main, which is our main actor. Then we have an aggregator bot, which we also only have one of. And then we are going to be spawning in a bunch of these counter bots, which the diagram only shows 2, but depending on how many lines we have in our file, each line is going to spawn an additional counter bot. So this is the main method of the program. What we do is we start up our one actor system in Akka, and then the actor system is used to manage and create all of the other actors that we need. And we're going to create the actor system with the type counter main, which is our main actor in the system. And then here, this is just a name for the actor system. One thing that Akka Actors and actor systems need is they need unique names. You can generate it with like adding on a random number to your like bot, or if you have bots that do like specific like purposes or computation on like a specific like ID of a file, then you can like add on that ID, but you need a unique name for actors. And so in our main method, what we're doing is we're reading in a file using source, and I believe it's in just in Scala. And we're reading in a file, which in this case is going to be sample.txt, which is this file right here. There's only 4 lines here. And then afterwards, we'll move on to a slightly larger example. But yep. And so what we do is for every line inside the file, we are going to send a message to our main actor. And to send messages in Akka, you use this exclamation mark symbol. And so on the left, you put the actor that you want to send the message to. And then on the right, you have the message that we're sending, which is just a message that contains this individual line. So then if we move up to the code for the counter main, we can see here that I create a random number or a random number generator, and I'll explain why that's being used in a second. This is the message that counter main is going to be receiving of type initialize message. So we can see here that when we make counter main, when we're making our apply method for it, it has behavior type initialize message. And so this is sort of the Akka typed thing, where in untyped Akka, you wouldn't have to specify a type for the behavior. And so Under the behaviors.setup section, this portion is only run once. And we log some stuff in the console. And then one time we spawn our aggregator and we save a reference to it. And then for every time that our actor main, or for every time that our counter main receives a message, we take that message, we create a counting bot, which, as I mentioned before, every Akka actor needs a unique name. And so to create this unique name, I took a string counting bot, and then I add a random next integer, which I don't remember the size of the maximum size of this, but this should work pretty well unless we're trying to read the largest text file in the world.
Your setup context, I don't know, maybe I'm looking at it in your screen, it's the wrapping may be messing with it, but can you scroll up for a second? I just wanted to see what the scope is. So you have your apply, and then, okay, I see what I think I'm understanding it now. Your apply context starts in 60 and it ends in line. Which line? Can you scroll down? Yeah, where does that come? Okay, I see. So that whole thing is being run once, right?
Yeah, and
Okay.
so if we have a line that has a behaviors dot something else,
Yeah.
what we're basically doing is we're changing the behavior of the actor. So behaviors.setup goes once, and then we get to behaviors.receive message. So now in the future, our actor has this behavior now. And then,
right. That's my question though. Wouldn't you have like behaviors.setup open and close context, and then you have behaviors.receive as a separate, or does it matter? It doesn't matter. Anything inside receive message is always going to be done when it receives a message, versus everything inside setup happens the first time, but it doesn't happen the second time. Is that
yeah.
Okay, I got it. Thank you.
And so, as we receive messages, we create these counting bots for each one of these messages. And then we take that reference to the counting bot we just made, and we send it our message, which is going to contain two components. It's going to contain the actual context of the line from the text file, and it's also going to contain a actor ref to the aggregator actor that we have. And that's important because once our counting bot does its counting of the number of words in the line, then it needs to know, or it needs a reference to the actor that it needs to send the results to. And since there's only one aggregator, when we make it, we save a reference to it, and then we just send it off in each of our messages to our individual worker bots, so to speak. And then at the end here, we have behaviors.same, which basically keeps so after a message is received, we do some stuff, and then behaviors.same is saying keep the behavior of the actor the same as what it currently is. So it'll just go back to this behaviors.receive message. And then this is the code for the individual counting bot. Again, it is typed. We know that we designed our counter bot to receive messages of type line message. So if we look back down here, where we sent messages to counting bots, we could see that we sent them messages of type line message. So that means that our counter bot has to be of type, or the behavior type of the actor has to be line message. And so every time one of these bots is made, we log that the bot has been made, And then as it receives messages, it will count the number of words in them. And then what we do is we then send the result of that calculation inside of a count message type, which in this case, the way that we're counting the number of words is we're using a regular expression to split up our string, which contains the whole line of the text file, into an array of the individual words. And then we're just saying send the length of that array, which I don't believe this is a very efficient method for doing this, but we're just gonna pretend like it is and pretend like we're doing real good, useful data processing, not counting words, which we could be, but in this case, we're not.
You're talking as if like the rest of the world actually does really good data processing. It's usually pretty crappy.
Well, benefit of the doubt. And so at the end of this receive message section, unlike in our example in the counter main actor, we end it with behaviors.same, which then in the future it will just keep doing the behaviors.receive message action when it receives messages. But in this case, for our counter bots, they are each designed to only have one line sent to them. And so in order to not clog up memory, because unlike in unlike in something, I guess, in like normal typical Java, where if you don't have references to an object anymore, then if you don't have references to an object anymore, then eventually garbage collection will remove it from memory. But in Akka, actors don't disappear automatically. So you need to tell them to stop, or they can error or crash, but you need to tell actors to stop if you want them removed from memory. So once our counterbot has received the message, it does their stuff with the message, sends off the results, and then its behavior is switched to behaviors.stopped once it reaches this line, which will terminate the actor, and then it'll get cleaned up by Akka shortly after. Yeah, shortly afterwards. So finally, we have our counter aggregator, which again, we only have one of. And so what's going on here is we have a private variable here inside of the counter aggregator actor, which is storing our current word count. This is one way to sort of keep up with a changing state. Another way to do so is if you look into Akka documentation and you see some of their like quick start examples, or like maybe one of the more involved examples, you can also modify the behavior of your actor every time stuff happens to it, instead of having a private variable that keeps track of whatever things are happening in the system. But this is just a by design thing. You don't necessarily need to have variables inside of actors holding stuff. You can modify behaviors in other ways. And you'll probably see that a lot if you look at examples of code and documentation, where you won't see a private variable inside of an actor keeping track of state. And so our counter aggregator, once it's created, it says in the console, the aggregator has been created. And then every time it receives a message, it takes that message, it adds to the private variable count that it has, then it prints the count, and then we keep the behavior the same. So its behavior goes back to this state, So it's ready to receive more messages and process them in the exact same way. So now I'm going to run the code. We make sure that we're reading from sample.txt, which is right down here. Another thing I want to mention is that the reason that it's so simple to read from the file and that I don't have to provide a path is that the code is structured in a particular way. So we have I know this text is really small, but if you look at the repo when it's available, you'll see that the main code is under source main, and then inside of some other files, and then under the source directory and then under the main directory, there's a resources directory. And if you place files inside of there, then you can read them just straightforward like this with just source.fromResource, which is convenient for testing stuff. And you don't have to have a path to the files that you're trying to access. So I'm going to run this code now. I'm not sure if I can zoom in on the terminal. I have not been able to figure that out, but I can just read out what's sort of occurring. So we can see that a bunch of stuff happened. And we see that it says at the bottom here, the current count is 27. We also see that there are 4 of these messages that display the current count, which is what we expect, because the count is only printed by the aggregator every time it receives a message. So our text file originally had 4 lines. We have 1, 2, 3, 4, 5. We have 10 words, 9 words, and then 3 words. So 25 or 27 is the correct number of words. And we can see that we got 27. So yay, we did data processing. And so one thing that isn't being logged is the fact that some of these actors are being shut down. So another, I guess, more proper way to do a demo like this, but maybe with like a larger scope of actors, is that once we've finished processing our file and done all of our counting, then we should also shut down the main actor. And so one thing I didn't explain earlier is that in Akka, individual actors can create other actors, but then those are called their child actors. And so if a parent actor happens to crash or shut down or die catastrophically, or is just told to shut down, then all of its child actors will also turn off. And so a way to end an Akka application is to shut down the main actor, which in our case would have been counter main. And then that would shut down all of its child actors. But at the moment, the demo does not do that. And so once you're done, you just need to like Control-C, or however you stop files, or however you stop things from running in your environment. And yeah. And then now I'm going to show off a, well, not very interesting file, but a file with a lot of words. So it's a file which has 400 copies of we have no problems with this file copied into it. So if we count the number of words here, 1, 2, 3, 4, 5, 6, 7. So there's 14 words per line. So 14 times 400 lines is 5,600. And now if we go into the program and change sample.txt to sample2.txt, and we clear the console, and now we run the program again, we're going to see an extremely large amount of debug messages. That's because I'm logging a lot of information here, so it's not super useful in when you have tens of thousands of lines coming in 1 second. Now some stuff happens, and hopefully we get 5,600, which we do. So you can see that something like this works for slightly larger files. Not a very practical file to count the number of words in, but it does work. And then one line I forgot to mention in the main method is that once we're done with the file, we just close the file. But that's not important to Akka or actors in general. That's just a Scala thing. And one last thing I would like to mention is that when you send messages in Akka, they are sent on a sent at most once principle. So Akka by itself doesn't guarantee that a message is actually received by the actor that it's being sent to. If you want to try and guarantee things like receival of a message, then you could use like wait for an acknowledgement, and then you would probably also want to so you would basically have to add in that portion yourself. And there is a section of documentation where they talk about this called message delivery reliability, where as I just mentioned, it says here the rules for message sends at most once delivery. So there's no guaranteed delivery. And if you want to try and change this to at most once, at least once, or exactly once delivery, then it requires different levels of effort put in order to achieve these reliability guarantees, where exactly once is the hardest. And I guess one other thing I should mention is that as we talked about before with typed actors, you have to define a type for their behavior. And so then that actor can only receive messages of that particular type. However, you might be asking, what if I want an actor to receive different kinds of messages, right? Which, well, is very useful. And for that, what you would do is you create a sealed trait, or something known as a sealed trait in Scala, and then you have your individual message types that you want an actor to be able to respond to, extend those traits. And then when your actor receives messages, you then pattern match and determine which one of the which type of message you actually received.
I guess you could kind of make a complex interface that has attributes, right, that make it rich. Like, so for example, having a structure where you have like a payload, you have metadata, right? And then depending on your metadata, you don't even have to do like Scala pattern matching. You could just like see what it is, and you can have a case switch statement for example inside your like main parent actor, right? And then depending on what you want to do with it, you could spawn child actors, right?
Sure. Yeah.
Like kind of like a classic facade or commander pattern where you just literally you process it and you determine what to do, and then you kind of direct the work to something else.
Sure. Yeah. All right. I believe that is all I have to show in this demo project. Again, we'll have this up in a GitHub repo, and we'll have a link to it in both whenever this YouTube video, or whenever this is posted on like YouTube, and also in the blog that'll be coming up in the next few days.
So at some point, I think you're probably going to cover Alpaca, right? What's the difference between like building your own processing versus using like Alpaca from your experience?
When I worked with Alpaca, I don't think I built anything particularly complex here.
Mhm.
I mean, also in Alpaca, I didn't really deal with like actors directly at all, or there were no actors like being done at all.
It did everything in the back end for you, so you don't
Yeah,
have to
yeah.
worry about
So
it. Okay.
I mean, here I guess I had to first plan it out. Like, had to go, okay, so first I'm going to draw pictures that show off what I think I want my system to maybe do, or rather, first I have a list of stuff I want my system to do. Then I have to create a picture of, okay, I'm gonna have this type of bot, then I'm gonna have this type of main actor. This is who's gonna spawn who with what type of message. Then you have to write out all the types first. And then finally you can start writing out all of your actors. So it seems a little bit complicated, but once you've written a couple actors, it's not bad. And I think that the type thing is a good thing, especially for if you're creating code that is ever going to be touched by anyone else. Then having actors be typed and only be able to accept messages of certain types, otherwise Akka will complain directly at you, is a very good thing.
Yeah, I mean, the whole type versus non-type discussion is, um, it's funny because it's the same discussion in different forms. So structured versus non-structured, in data. So people are like, oh yeah, I don't really need a schema. Like, well, eventually you kind of do, because if you're going to have an API has a schema, right? You have a contract between what people are calling it as. So, well, I want to be able to change it. It's like, yeah, every time you change it, you're changing your contract. So you have a schema. You think you don't have a schema, but you have a schema.
You do. Yeah.
Or eventually when you come to the programming world like this, and it's like, life is actually easier to have typed cases, because when you compile at compile time, you know that it'll all work together. And because you've made sure it has the same type, you can have different systems using the same type, and they'll all talk together, regardless of whether you're doing something like REST. One interesting fact, Spark used to run on Akka. It was actually built on Akka, and so until Spark 1.6, which is like old now, we're at Spark 3 now. It used Akka for communicating the different systems together, right? And basically had Akka Actors coordinating the computation. And once the data was there, it would then send the data back. Now it has its own remote procedure call engine, because they just didn't want to have a dependency with something else, because Akka would progress at a certain rate in versions, and Spark was progressing, and to have type, for the reason for what we're talking about, for having typed safety between two versions of Akka, it's like you have to have the same version of Akka, right? And so they ended up saying, well, we don't necessarily need to be as structured, because what they were passing was like, do this work, and then when the work was done, it was saying, okay, I got the data done. Here it is, and nothing special beyond that.
I did not know that.
Yeah, no, absolutely. That's how I learned about Akka when I was playing with Spark, and like, what is this Akka thing? And so I started deep into it, and it was like, oh, it's like a world in itself. All right, Akka it's a world in itself. I mean, the other, I think, fascinating thing about Akka is that it's the core basis, right? It's the core basis. There's other things on top of it that people use, like Alpaca. We just talked about that. Play, which is a web application framework on top of Akka. Under the hood, it's all actors. There's a thing called Lagom, which is for microservices. I mean, technically, an actor is a microservice. It does one thing, right? You give it a message, it does one thing, and it's done. So if you can imagine, like, wrapping an actor in a REST API, right? It's perfect. It's a perfect microservice. It just comes and goes. But Akka, I think, was the ultimate like serverless function, basically, because I don't think you covered Akka clustering, but like you can have this code run on like many machines, right? And it will basically work.
Yeah,
that's a different work.
I did not cover that. That's true, but that is a thing that exists, right? That's part of the whole Akka helping you build distributed applications thing.
Yeah. Yeah, it's pretty advanced stuff, but as you said, like once you get into it, it's not that complicated. So it's like riding a bike, right?
Documentation's good. Documentation is good.
Oh yeah, for sure. Yeah, people use Akka in the stock market because like next to C++, Akka is the best way to have real-time stuff happening all the time. And where like each actor has a particular state, the state of the system is the state of the system. Like there's no other place where you can get data except by talking to that particular actor that's doing some computation or doing some particular trade. And then in I think manufacturing would be the second place I would think it has the biggest use, is in that it is as close to the hardware as possible, like the robotics, and it's talking via very, very lightweight messages, and there's nothing around it, right? It's just the JVM. So it's like a pure engine that just does work. So yeah, I feel I geek out about it. It's like the possibilities, the possibilities of what Akka can do are just untapped by most people. Like you can build anything on it. It's just, why would you want to if there's other technology that already exists?
There are good examples of large companies starting to at least use Akka though.
Yeah.
So it seems like people are figuring out what's going on with Akka and actor model in general.
Yeah, well, the SMAC stack, right? Spark, Mesos, Akka, Cassandra, and Kafka was the original distributed stack that involved Spark and all of that stuff together. It made Akka more popular beyond just, it was running Spark. And once it became popular in that realm, people realized that, you can use Akka by itself. You don't have to use it with Kafka. But if you do, basically you have a persistent engine for messaging, for example. So even though you're using Akka, you can have Akka actors do most of the work, and you can use. And also there's like something called Akka journaling, where it will take every message that it's getting and it'll save it to a persistent store using Akka persistence.
Right.
So you can save everything into Cassandra as a state, or as every change that's happening on the actor. Unfortunately, it's not like very reportable. Like I think it's a serialized format of the information getting saved in there. But what it allows you to do is to potentially replay everything that has gone through that actor. You can have it replay that because it's persisted every single message that came in.
Right.
So it's cool stuff. Sorry, I've like hogged all the question and answer time.
All right.
All right, folks. Sorry we didn't have too much time for Q&A. Great presentation, Nikita. Looking forward to the follow-up on this. There are some use cases where I've seen it used for like data mining, like web crawling, which is a perfect use case for this, right? Like go to a page, find the links. So I'll send you that. Maybe we can tie that in with some of the stuff we're doing with leaves and like see how quickly we could crawl the world. No, I'm just kidding. Good presentation. Thank you so much. All right, folks. Have a wonderful rest of the week. We'll see you next week, same time, same place. And maybe I will pick up that thread on Akka and do a presentation next week on it. All right, take care, guys. Bye-bye.